Welcome everyone to this talk, which is about open source software for eSIM integration. The premise of the talk is that we assume you might be involved in development of an embedded device that has some form of cellular connectivity. And traditionally that would have a slot for a SIM card, a physical SIM card that gets placed and replaced by the user. And if you now want to move that towards eSIM, so how do you do that, and especially how do you do that using open source software rather than some proprietary solution? Yeah, so this is a, I guess, fairly technical talk. And in case you've never been to a presentation by me, it's very text heavy. I'm not a graphical person. I apologize in advance for not having fancy slides. I guess the command line usage sort of shows. Okay, if that doesn't discourage you from attending, great. I've been doing Linux-related stuff for quite some time. Have been a bit out of the Linux community in recent years since I focused on open source software implementations of telecommunication protocols and protocol stacks and stuff like that. There is a community project called sysmocom. If you're interested in cellular technology, you might want to check that out. And I run a small company called sysmocom, where we do professional development services and products around these open source cellular technologies. Okay, so before we go into eSIM, let's recap a bit the classic SIM. So classic SIM was introduced, by the way, SIM is subscriber identity module, in case that is not known, was introduced with GSM, the 2G technology first introduced in Europe in 1991. It's a single-purpose contact-based smart card, and it has primarily the purpose of, well, today not so relevant storage of storage of contacts not so relevant today in SMS, but storage of configuration data still is extremely important today. And the most important functionality of this subscriber identity module, well, as the name implies, is to identify the subscriber by cryptographic means. And that means there is a secret per subscriber key. Well, there's actually multiple, but one very specific important one for the authentication of the subscriber towards the network. From the 3G network technology onwards, that's UMTS or WCDMA if you're US-based, technically it's a USIM and not a SIM anymore. Everybody still calls it a SIM, but SIM is a term that refers specifically to a 2G technology, and the USIM is the successor for UMTS, LTE, 5G, and up to today, everything that followed. So I'm using that term here in the slides, the technically correct term, so just don't get confused. Colloquially, it's a SIM. I will always refer to it as USIM. And the USIM was specified as a logical application on top of a UICC. The UICC is the physical chip, and the USIM is an application that runs on the UICC itself. So, and that will become relevant later on in the presentation. So ICC is the integrated chip card, UICC is the universal integrated chip card, and the USIM is the UMTS subscriber identity module. So, now what has changed with eSIM? eSIM means embedded SIM. And by the way, just for fun of it, I always like these kind of nitpicking anecdotes. It's called eSIM, but we just learned that from UMTS onward, it was a USIM, right? And believe it or not, the eSIM doesn't actually have the capability of a 2G SIM. It only has USIM capability. So there you go in terms of naming confusion. Anyway, so the eSIM is actually the virtualization of the USIM, so of a subscriber identity module that's capable to authenticate UMTS and more recent technologies. And what happened there is the decoupling of what we always called in that industry the SIM profile from the physical chip. So the SIM profile is basically the data that is stored on a USIM or SIM. In a traditional model, the USIM was a basically inseparable combination of a cryptographic smart card controller with an operating system and that data on top. And you could only buy that from an operator as a single device, and you could not separate those two, at least unless you break the security mechanisms, which didn't happen all that often. So in eSIM, we decouple those. And the eSIM-capable chip, the hardware that's in the device, whether it's an embedded device or a phone or something, is the eUICC, the Embedded Universal Integrated Chip Card. And the eUICC can now hold one or multiple eSIM profiles, which are the logical SIM functionality in that chip. So yeah, just the relevant acronyms and elements in that universe. So the eUICC we already heard about. It's the classic chip card that is used for eSIM and other purposes. We have the eUICC now. That's the one that has the eSIM capability. The eSIM is the SIM first introduced with UMTS, and now we have two more acronyms on that slide, which we'll have to remember. That's the SMDP+. That is the fancy word for the server from which you download eSIM profiles. And there is the LPAe, which is the software, the client, basically the software that downloads the eSIM from the server. So SMDP+ is a fancy term for server, and LPAe is a fancy term for client. And if you install an eSIM profile on your phone, then on your phone you have software that will facilitate that download from the server, that with the user interface where you select, where you enter the QR code and or select something and so on and so on. That is the LPAe software, and that sits in between the server from which the eSIM profile is downloaded and the eUICC chip that's inside the phone. That's sort of the different concepts here. In terms of terminology, unfortunately, especially the marketing side, but sometimes even the specification side, is using confusing language. I always say eUICC when I refer to the chip because that's undoubtedly correct. When people say eSIM, sometimes they mean the eSIM profile and sometimes they mean the chip. That's super confusing. That's why I always say, well, eSIM profile or eUICC, and then I have very clear terminology about what I'm talking about, because eSIM can really be either. Yeah, so what is that eSIM profile that we download? It's, well, you can think of it as a glorified tarball of the file system contents of the eSIM, because SIM cards have a file system. And some metadata like the authentication key material. It also can contain executable code that depends on the operator, so-called Java applets, or actually more technically specifically Java cardlets. Just like in the classic eSIMs, isn't really relevant to use, just for your information. That eSIM profile is downloaded via the LPAe into the eUICC, into the chip, and there then it's parsed and it basically rebuilds the file system from that tarball. You can think of it that way. Of course, it's completely different data structures and so on. It's signed by a hardware security module in the SMDP+ in the server, so the eUICC can verify the authenticity that it's actually from a legitimate server. And it's also encrypted with the private key of this specific eUICC. So every eUICC that gets produced contains a private key and a corresponding public key that is derived from a PKI. And the SMTP+ will encrypt a given eSIM profile with a specific key material for one eUICC to make sure that no other eUICC can use that unless somebody manages to extract the secret key of the eUICC, which breaks the entire security architecture, but which has happened recently, so it's not completely unthinkable. Yeah, so before that download happens, that's what every user, I guess, knows, is if you install an eSIM in your phone, you have that activation code, usually as a QR code, but sometimes also as a string representation, text representation, and that is sort of the token which you use, or which you give it to the LPAe software, to the client. The client then extracts the host name from that activation code. It starts the download to the SMTP+, or the download from that SMTP+, and the activation code contains a token that sort of matches the business process of you buying an eSIM with an actual eSIM profile that then gets downloaded into your device. Okay. That's sort of the big picture. Now looking at the eUICC itself, the chip. So when this was standardized, it happened in a way that it's used the same electrical interface, just like a eSIM. Also, the data transmission is like a eSIM. And in fact, an eUICC, once it has an activated eSIM profile on it, externally looks just like a eSIM. So the phone or the modem, the cellular modem in a device doesn't need any modification to use an eUICC with an activated profile to register to a network and do whatever things it does. I mean, in fact, a modem or a phone doesn't even I mean, it can know, but it doesn't need to know whether it's an eUICC or a physical card that it's talking to. And the mechanical form factor usually is soldered instead of pluggable, but that's just usually. So you can have an eUICC that comes in the same plastic form factor like your classic SIM card that you can plug into a device that is not natively eSIM capable. And that brings some interesting points. So it brings me to the removable eUICC. So as I said, it's the same chip, it's just different software on that chip. So you can package it in either the solder type package, or you can package it in a plastic form factor. My company is selling such cards, but you can find other vendors, of course, if you Google for the right terms. It can be useful for R&D, testing, debugging, but it can also be useful to retrofit existing devices without doing any hardware modifications. That's, of course, useful in that context. So eSIM comes in 3 flavors, which do not really have much relation to each other. So that's always something to keep in mind, is if you talk about eSIM, you need to be sure whether you're talking about the machine-to-machine eSIM, the consumer eSIM, or the IoT eSIM. Now, I didn't make up those names, right? But the technical terms, I mean, the specification numbers are presented in the beginning. They're listed in chronological order at which they have been invented. So the original design was the SGP.01 and 02 machine-to-machine eSIM. It's not, well, I'll get to that later. The second development was the consumer eSIM, which is basically what everyone knows if they have ever installed an eSIM on their phone using a QR code. That's the consumer eSIM. And now there's a new, excuse me, a new flavor of eSIM, that's the IoT eSIM. And protocol-wise, for example, the M2M eSIM and the consumer eSIM have nothing in common, 0. Completely different systems, different protocols, different layering, different everything. The IoT has some overlap with the consumer. Now, as I said, I'll get back a bit on those details, but let's focus on the consumer eSIM now, because that's sort of the only thing that you can get today at minimum order quantity 1 from virtually any operator. So therefore, it is, from my point of view, the most interesting technology. And in the consumer eSIM model, the design idea was the smartphone or tablet or whatever end-user device concept, where we have a pull model, where the local user in front of a user interface, in front of the cellular-enabled device, makes a decision where to buy an eSIM and then actually to install it onto the device. So the control is decentralized and it's delegated to the local user in front of a device. That's the consumer model. I'll spare you the details of the diagram. The relevant parts here are the SMTP Plus, the server that we have been talking about. Then we have the device as the gray box here. The device contains an eUICC, that's the physical chip. And then we have the LPAe here and LPAD. I spare you again the details. That is the client software that sits in between the server and the eUICC. And that's sort of the relevant parts here. We already have been talking about the eUICC, we know the SMTP+, we know the LPAe. The only addition from that slide is, well, we have a very exotic encoding. So for people who are interested in communication protocols and APIs and interfaces, I find it rather, how can I say, charming that you take ASN1 DER encoded blobs and then you put them in base 64 and then you put them in a REST-style JSON interface, which... Well, why not just put the ASN1 into HTTP if you want to use HTTP? So that additional JSON layer serves exactly nothing, other than increasing complexity. And I guess maybe you could get a patent more for the exotic combination of protocols. So the SMTP Plus now is the server. It's the secure server, and it mutual authenticates, as we already have established with the eUICC, the chip. It creates the profile that contains some data that's identical for all of the subscribers of an operator, but then also the subscriber individual data like the IMSI, the identifier number, or the key material, and so on. Signs and encrypts that, and then it gets downloaded to a specific eUICC. And once there's a step in this is called profile binding, and that sort of binds a logical eSIM profile to a specific eUICC, and once that has happened, it has happened. So you cannot download the same eSIM onto another eUICC ever. There are some business processes that give you the illusion of that, but technically, an eSIM profile, once it has been bound for the first time, it's indefinitely bound to a specific eUICC, and if you move to another device, you need a new eSIM profile that may be associated with the same contract, a subscription or something at the business logic level, but technically it's not the same eSIM profile. Yeah, the SMTP Plus are most often operated as a software as a service from separate companies that are independent from the mobile network operators from which you obtain subscriptions. So the mobile network operator would contract with an SaaS provider that operates an SMTP Plus on their behalf. And that relates to the, security requirements that relate to it, which I guess we'll get to at some point, unless we run out of time. We won't. The LPAe, the local profile assistant, that's the relevant part the most relevant part in the context of this talk, since we were thinking of eSIM enabling an embedded device. So that's the client software that needs to be running on your embedded device. There is actually an option where the LPAe can be fully built into the eUICC. That's called an LPAe, an embedded LPAe. I'll skip it for the range of the discussion because it's a bit exotic. The standard case is that you have an LPAD, the LPA on the device, so you have a piece of software that in this hypothetical embedded Linux device would be an application program running on Linux, and it would be an open source one in the context of this talk. It talks to the eUICC and it talks to the SMTP Plus, to the server and to the chip. The operations that this LPA software has to implement are first and foremost profile download, which is what I've been talking about all the time, downloading an eSIM profile from a server from the SMTP Plus into the eUICC. And then there's so-called local profile management operations, such as enabling a profile, disabling a profile, and deleting a profile. And last but not least, processing of notifications. So enabling and disabling is pretty straightforward. Deleting also is obvious. If you've deleted a profile, it's gone. It's deleted. In terms of enabling and disabling, almost all the eUICCs you can find today are version 2 of the consumer eSIM specification, where you only have a single enabled profile at a time. So you have one eUICC, and you can have any number of profiles until you exceed the storage limitations of that chip, but only one of them can be active at a given time. In version 3 of eUICC specs, you can have something called MEP, multiple enabled profile, that is used in the context of multi-eSIM devices. You may remember dual SIM phones with 2 physical slots, and that's basically the same in the virtualized world. So a phone manufacturer or device manufacturer doesn't have to solder multiple eUICCs next to each other if they want to have that capability, but they can run that on a single chip. But as I said, for the majority of the use cases today, there's only one enabled profile at any given point in time. The processing of notifications, what's that? So basically the SMTP Plus, or actually the mobile operator that has issued that eSIM, may want to know whether a download has succeeded or whether it has been enabled or disabled or deleted from a device. And that is done by notifications that are generated inside the eUICC. They are cryptographically signed, again, by the eUICC, so they can be authenticated. And then those notifications are retrieved by the LPA client software and uploaded to the SMTP Plus server, so that the SMTP Plus knows about it, who can then notify over other interfaces the actual mobile operator who has issued that card that it has been deleted, for example, which then can trigger you to be able to order a new eSIM profile for that subscription because the previous one has been deleted, and there's a cryptographic proof that the deletion has happened, which is in the eUICC, so unless you can compromise that one, nobody can spoof that. Yeah, a bit about the security, just so you know the bigger context. So there are security accreditation schemes by GSMA. GSMA is the operator club. So basically the group or the entity that represents the interests of the mobile operators around the world. It is not the specification body for all the other cellular technology. That's 3GPP and ETSI and the members of 3GPP. So the GSMA is a bit odd for having such a odd place from my point of view for such a technical specification, but that's a separate discussion. In any case, there is a security accreditation scheme, and actually two of them, one for SMTP Plus for the servers and the other one for the UICC production, the UICC manufacturer. And it's very comprehensive. It's lots and lots and lots of requirements, not just about whatever software architecture or that, for example, the operating system must be EAL4 Plus in the UICC approved. But also things like what are the physical access requirements for the co-location site in which your servers reside, the fact that the cryptographic material must be in HSMs according to a certain FIPS 140 level, and so on and so on. But it also, just to give you an idea how seemingly paranoid they are with that security, is that, for example, the server that runs an SMTP Plus, it can only get accredited if there's no remote SSH access to it. So the only way to let's say, do an update or to modify or to do something on that server is if there are two people, so 4i principle, physically on site in front of the server, which had some interesting challenges with COVID restrictions back in the day, but in any case. So a lot of also, process and whatever business related requirements. Sadly, not all the necessary technical requirements from my point of view, but that's again a separate discussion. But yeah, so if you wanted to operate your SMTP Plus, you're happy to do that, but you won't interoperate with any of the eUICCs that have been issued because they only accept eSIM profiles from an SMTP Plus that is part of the certificate authority operated by the GSMA. I mean, you can issue your own eUICCs that contain your own key material, and then you can operate your own SMTP Plus server, but then you're in your own bubble and you cannot install a T-Mobile or Vodafone or whatever eSIM profile on it because their profiles only get installed into GSMA derived key material and certificates UICCs. So that's sort of the, well, there. So okay, so what can we do in terms of open source software? Well, all those protocol specs are public, and even without any registration, everyone can download it, so that's nice. In theory, you can implement all of that in free and open source software. In practice, operating the server side has a huge cost associated to it due to the accreditation. I don't recall the details. I guess it was around 20,000 euros a year only for all the audits, if you pass all of them. So just to give you an idea about and that doesn't include the cost of actually producing something that fulfills those requirements and documenting it. So yeah, like a production SMTP Plus in open source software is much less likely, but the LPAe, the client side, there is no need for any accreditation or approval or something like that. It's just a piece of software that anyone can write, and therefore we have open source implementations. We have LPAc or LPAc, whatever you want to pronounce it. It's available on GitHub. It's the primary developers of this are all some Chinese hackers. So that is unusual for many open source projects, I would say, but they've been very active in this field. There is LPAe Desktop, which is something that TruePhone, an eSIM issuing company, created at some point. That's a GUI application, and in terms of SMTP Plus, actually, I wrote an SMTP Plus for testing and hacking purpose, but of course, as I said, you can't operate that productively due to the GSMA requirements. So the LPAc, which we'll cover here, the local profile assistant, LPAc because it's written in C. So a standalone open source project that implements this functionality. It has so-called drivers. One driver is towards the HTTP, so you can bind your operating system's HTTP libraries to it. And the other is the so-called APDU driver, and APDU being the message that is exchanged between the eUICC and the LPAe. So in general, APDUs are the commands and responses that you send and receive from any smart card in general. So it's an underlying concept of smart cards. So basically, the C code, you can have an HTTP driver for whatever HTTP library you want, and you can have an APDU driver for whatever way you can talk to the UICC chip. and therefore it's rather portable. They have some integration for Windows, for Linux, for Mac OS, for Android, for Linux Mobile. We also have the person who did that in the room. The interface towards an application like a user interface is rather curious because it's JSON that gets printed to standard output of that process. So basically, if you want to do a profile download, you execute a command and you give it the command line argument of the activation code, and then it will report output to the standard output of the program. But you can integrate that nicely with any other software. You just pipe that in another file descriptor and so on. So if you're on a desktop Linux, then you can just compile it, and it will use a driver for PCSC Lite by default. And that driver means you need a chip card reader like the one displayed down there. And you can either have a plastic eUICC, or you can actually have there's adapters for the solder type packages. So you can also access those from a laptop if you want that. So the profile download looks like something like this. So I'm calling the LPAc executable as a profile download. That's the command. Then the SMTP plus and the matching code. Those two are basically things that are retrieved from the QR code. So if you decode the QR code, it will tell you those two values. And then the JSON that you can see is the progress output that gets returned on standard output of that process. In the successful case, of course, here. And the same is, well, you have commands like listing the profiles, and I just use JSON PP, so we get a nicer rendering here for human users, and it will show you there's 2 eSIM profiles on that device and some parameters about it, like the name and things like that. Similarly, for enabling, disabling, and deleting profiles, rather straightforward. You just pass it the ICC ID, which you got from the list here. You see the ICC ID fields in the JSON. You just use that for enabling, disabling, or deleting it, and then you can manage the profiles that way. So rather straightforward. Now, from a laptop with a smart card reader, that's nice, right? That's easy, but that's still not our embedded device. So we need to look at how do we integrate that into embedded devices. And as I said, the premise, I don't need to repeat that. So we need to equip our device with an eUICC, whether it's plastic or solder type, but then we use the LPAc software, and then we need that LPAc to somehow access the eSIM in the device. Replacing the hardware, well, okay, either use the plastic card or use a solder package. They look like this. This is a standard form factor MFF2. But now we have the question, well, we have a cellular modem, and the eUICC is attached to the cellular modem. How can we reach that from our LPAe software so that those two can talk to each other? There are basically 2 major models how you do that. On the one hand, there is AT command-based transport. As anyone who has worked with cellular modems will know, that's sort of the legacy that goes back to the Hayes modems of the 1980s, and other analog modems, of course, at the time. And there's a 3GP specification called TS27007 that specifies the AT command set of cellular modems. Often vendors have proprietary extensions, but sort of that's the basis. And there are 3 AT commands that relate to opening so-called logical channels and exchanging APDUs over those logical channels of a SIM card or an eUICC. That doesn't really matter. It's the same all over again. So you can use AT plus CCHO to open the channel, and CCHC to close the channel, and CGLA to exchange APDUs. And LPAc already contains a very simple but currently reworked driver for sending such AT commands. So basically all you need to hook up is somehow your serial port or whatever virtualized serial port that you speak AT commands over, and then maybe work a bit to speak the exact dialect of your specific cellular modem vendor, because sometimes they have some misunderstanding of the standard, or, for example, the standards do not define data types. So we had this incompatibility. TS27007 says, well, there is an integer, and it's represented in ASCII, but do you print it as decimal or as hexadecimal, right? And then you have 2 implementations of that. Well, yeah. Of course, there's no range either. It's an integer, you know. Okay. And then there is actually one vendor that uses 64-bit hexadecimal representation, and of course not everybody has expected that when there's an integer. Okay, anyway, so that's AT commands, and the other commonly found option is QMI. That's the Qualcomm-specific interface, and it has a sub-module or a well, not sure what's the subsystem called UIM, User Identity Module, and LPAc also already contains support for that, thanks to Luca, who is in the room. There are, of course, other vendor-specific proprietary mechanisms depending on your modem, but all you would need to do is write that APDU driver. That's just a few hundred lines usually to establish that communication to the eUICC. Now we are close towards the end. Just one slide maybe about testing eSIM support. If you want to test that, it can get rather expensive rather quickly if you work with production eSIM subscriptions, of course, which cost money. So there is actually a GSMA specification called SGP.02 which uses test certificates, so a separate set of separate root of trust, a separate certificate authority, and it's a certificate authority in which the private key of the root CA is publicly disclosed. So in that context, you can buy eUICCs that are derived from that certificate authority, but everyone doing testing can also create their own eSIM profiles and interoperate with that. And so you can buy eUICCs with such specific test certificates on them instead of the production ones, and then you can basically either run your own SMTP Plus using existing open source software and do thousands or millions or whatever of installation cycles as much as your test needs, and you can also, we're also running a public instance of that. You can just point it to test RSP sysmocom DE. Of course, in that context, you won't get cellular connection to a public commercial cellular network. I mean, if you have a lab network, then you can, make sure the credentials match, and you can actually register to your lab network, your cellular lab network, using such a test eSIM profile, but not, of course, your commercial cellular operator. Now, one slide about the machine-to-machine and how it differs. The difference is that it's centralized from the device perspective, remote control. So there's a central server that determines which eSIM profile gets installed on which device, which is, well, yes, what you want in a machine-to-machine scenario, unlike a consumer model where you have a human being in front of a phone they own. It does not need an LPAe, it has some other constraints. The biggest problem is it cannot download consumer eSIM profiles, which are the ones that you can get everywhere from any operator. So you need special machine-to-machine subscriptions, which usually involve minimum order quantities and volumes and so on. And sadly, and that's the biggest problem, is it did not deliver on the promise of easily migrating from one mobile operator to another. And if I'm arriving at that point, then what's the entire point of using eSIM? Right? I mean, the point of eSIM is that I can remotely switch the operator in order to optimize cost or whatever, for whatever strategic reason, switch from one operator to the other. And sadly, the M2M eSIM did not deliver on that with all kinds of excuses by the involved entities, even though specification-wise it's possible. And that's what led to the new IoT eSIM model, which the first products are now appearing in the market. And it basically is designed in a way that you can use consumer eSIM profiles. So the operator doesn't really know whether it's the eSIM profile is used in a consumer device or an IoT device. So therefore you have the choice of all the operators, and you can mix and match, and you don't need to have all your devices at one operator and have a very hard time migrating it and so on. But it sort of centralizes control. So it's like the consumer model with centralized control, and that centralized control is achieved by splitting the LPAe in two halves. The lower half is still in the device, and the upper half is a new server called the EIM, the eSIM Identity Manager, I guess it is. And there's some additional cryptographic tricks so that even if a device gets compromised and the LPAe, which is now called the IPAe, is manipulated and is compromised, it cannot spoof anything towards the backend. So there is cryptographic signatures of the eUICC itself involved in operations like enabling and disabling, which is not the case in the consumer. So it's a slight modification. So that, I think, will be the big game changer in the IoT market. Yeah, and that brings us to the further information links, which will be in the slides, which I will upload to the website, of course, and we have a couple of minutes for questions and answers. Thanks for your interest. Do we have questions? I believe there should be a microphone somewhere. I'm not sure if there's... I saw a handheld microphone some time ago, but I do not know where it is. Thanks for helping out. Yeah, thanks. Thanks, Gerd. Not enabled.
Maybe I just use my voice.
Yeah, I can repeat it for the recording. Yeah, go ahead. Yeah, please. Yeah.
Thanks for the talk. I think it's a bit of a weird situation right now because, like, if I talk to people that hand out SGP.02 something cards now, they only support like the eIPAe version of it, so everything is running on the card in terms of management. And for the LPAe, like only the component running on the device ever got traction. And now at the moment I'm asked. Sorry. I'm asked by people whether it would be like a good idea to port something like LPAe to Sapphire or something and just use it because you can only get like the eIPAe implementations. Is that something you think would be feasible or a good idea to do?
So in terms of the available eUICCs, I mean, at the moment it's difficult to say what will be commercially available because it's all like only the first products get accredited right now. But in terms of, I do have eUICCs that support the IPAe external, so for development. And also at sysmocom we've developed an IPAe, so the IoT LPAe variant, which will be released as open source, I guess, in August. Well, it is August now, so actually, yes, it. Well, there was a date, so it should be released soon. Sadly, it only implements an earlier version of SGP.02, not the 1.2, which is the actually like the latest version, but. There will be some code released, but independent of that, I'm fairly confident you will find at least one vendor of eUICCs that will support the IPAe-D, so that is the software that runs in the device, as opposed to the IPAe that is inside the eUICC. But yeah, how much that will be used in practice, that's. But it will be available.
That sounds like good news then. Thank you.
Any other questions? Yeah, here in front. Well, thanks for the impromptu mic.
Thanks for the talk. Who would be running this EIM server? Would that be the device manufacturer or someone else?
The specs leave that open. I mean, from my point of view, the only, how can I say, the true benefit of this entire IoT, eUICC or eSIM scheme is if the EIM is operated by whoever is deploying the devices in the field. Anything else to me doesn't make sense, because then you have again control that is with some third party that let's say the device owner or the device fleet owner must trust and has dependencies to, and so on and so on. GSMA has pushed, or basically has released a security accreditation scheme for the EIM, but technically there's nothing that requires you to do it, because the specs are written in a way that anyone can run an EIM, and if you in your devices basically in the eUICCs you install the certificate of your own EIM, then there's no requirement for any GSMA root of trust in that, so that's possible. And actually, that's also something sysmocom has been working on privately, and we have sort of a grace period before releasing it publicly, but it should also be any day now, basically, since it's August 25 now. We have developed an eIM as open source. Sadly, again, it's version 1.0 and not 1.2 of the spec, and they have made a lot of changes. So there is a significant effort of getting that from the early version to the actual today's version of the specs. But I would say, from the control and dependency and avoiding vendor lock-in and so on, you would want to run that yourself. I guess there's also a model where you can have an independent SAS provider running the eIM for you. I can see that, but I would not I would not feel comfortable if the eIM was co-located with the SMTP Plus, who is contracted by the mobile operator, because then again you have this that's all one entity, and right, as a device fleet owner, you want to move away from one entity that is not you being in charge or having their fingers on this.
Is there a minimum amount of profiles which is possible to be stored in the eUICC, or the minimal amount of storage?
There is no such requirement as far as I know. I have read all the specs. I don't recall there's any minimum storage requirements. In practice, I don't think I've seen anything that has less than 300, 400 kilobytes of storage. And the eSIM profiles I've seen, the small ones are like 4 to 16 kilobytes. The large ones that include several Java cardlets for whatever reason are maybe 130, 160 kilobytes or so. And you can get, at the moment, eUICCs up to 2 megabyte of flash, for which some portion is required for the operating system, so maybe about 1.5 megabyte of free space. That's sort of what's available in the market. And the problem there is that you cannot get secure smart card chips with more memory that require that fulfill the security requirements. Sort of.
So at least 2 or 3 different providers and profiles are possible with all the hardware.
Much more. So in reality, it's more like 15 to 20 or so. We have some customers that actually want more. I think we've done a product with 80 or 100, but that's very special use cases.
What kind of flash when it will be destroyed?
So the question was, I'll repeat it, it's fine.
I talk about bad blocks of a flash device.
Do you
have some statistics or some experience what's happened?
So the question was about what happens if the flash goes bad, basically, in the eUICC. Well, it's the same like in the SIM. It becomes unusable when it goes bad. The question is, when does it happen? And there you have to check at the data sheets of the specific chip manufacturers. I mean, you can, and also, of course, the operating system running on the eUICC. So basically, you need to talk to the eUICC vendor. They don't publicly disclose that. It's under NDA usually. But for typical use patterns, I think we are. I mean, of course, it's hard to simulate. I mean, you can simulate the amount of writes and so on. It's a bit difficult more to simulate the aging of the device, but I think they're at between 20 and 30 years or so is the expected. Of course, it also depends on the usage pattern. It's always very hard because, for example, the update frequency of the eSIM depends not only on the operator but also on the amount of mobility of the device and the specific configuration. So there's so many variables in this. It's very hard to have a general response to it. Okay, good. Then thanks again. Or do we have other questions? Sorry, I didn't see any more hands. Oh, there's a hand. Yeah, guess we can do that. Yeah, slightly over time, I think, but I think it's okay.
Okay. Just now you mentioned about the version 3 of the eUICC. Can I ask what's the main use of that, or like the real life use case of such of a feature to enable profiles at a time?
Yeah, so if you think back some 15 years or so, there were these dual SIM phones, right, where you can install 2 physical SIM cards. And if you want to build something like this with 2 eSIMs, and the dual SIM phones, they came in a flavor that they have actually 2 basebands, and you can have 2 connections to 2 different operators at the same time. And if you want to do that in the eSIM world, Before version 3 of the spec, you would actually have to solder 2 physical eUICCs in the device, which doubles your component cost and doubles the PCB surface area occupation. And with the multiple enabled profile, you can have a single eUICC, but have 2 enabled profiles for 2 physical or virtual basebands that have 2 concurrently active cellular connections.
But this would require support from the modem as well. Is that
Yes.
so?
Yes, it needs support from the modem because there's an additional, let's say, communication multiplexing layer because there's only a single UART connecting the baseband with the eUICC, and there's a new multiplexing layer introduced that you can have these 2 concurrent eSIM profiles over 1 UART, basically.
Okay, thank you.